AB Calculus BC, Unit 8, Day 3 office hours. These are the even problems. Go ahead and check them real quick. Pause the video if you need to. Should check your odds in the back of your book. All right, so let's try some of these. So the first two are exploration problems on page 480. So first one says finding a power series for inverse tangent of x. It says number one of the exploration. It says find a power series that represents 1 over 1 plus x squared on the interval -1 to 1. So for this, you say, okay, well, the a value is 1, r value is -x squared. We've been doing this a lot lately, so we're getting pretty good at this. We could write the closed form. Usually it's the first term times the r value to the nth power if you start at n equals 0. If you start at n equals 1, then it needs to be n minus 1. First term should be 1. All right, this is your a. This is your r. So s equals a over 1 minus r. So you get 1 minus x squared plus x to the 4th minus x to the 6th plus ... plus -x squared to the n power plus ... That should equal 1 over 1 plus x squared. Okay, cool. That's part 1. Part 2 says use the technique of example 5 to find the power series that represents inverse tangent of x. So that technique was integrating this series. So using integration. So we integrate both sides. Dx, dx, and we get inverse tangent of x. And that's going to be x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus ... plus -x squared to the n plus 1 divided by n plus 1. What you should probably do is just take the negative out and leave it as -1 to the n. Take it out so that it stays the same sign. So there we go. If you're writing closed form, if you start at 0, so this is going to be your new nth term. So x squared to the n plus 1 over n plus 1. If we would have to start, actually, oh, okay. Well, I don't know. We could simplify this. This is, so, you know what? I think I might have made a mistake. If you rewrite this as -1 to the n times x to the 2n. So if you increase the exponent, you'd have to do like some u substitution stuff, which I don't think you want to deal with that now. So what you would get is you get x to the 2n plus 1 over 2n plus 1. That would be what you get. 2n plus 1, 2n plus 1. -1 in front, going to infinity. You need first term to be positive. First term also needs to be x. That's perfect. Okay. Let's see. Okay, part 3. Graph the first 4 partial sums. Do the graphs suggest convergence on the interval -1 to 1? So we're going to graph these. So on a graphing calculator, we're going to graph inverse tangent. Make sure you're in radian mode. Okay. Should keep typing all kinds of stuff I don't want. Okay. Now it says graph the first 4 partial sums. So that would be the first 4 terms. So that's going to be x minus x to the third divided by 3 plus x to the fifth divided by 5 minus x to the seventh divided by 7. That's the first 4 partial sums. The window, I think, I don't know. Let me just try -5 to 5, -5 to 5. I don't know what it's going to look like. So that should be inverse tangent. Okay, yeah, it looks like inverse tangent, sort of like a sideways. Now here's that curve. Look, it hugs it pretty well between -1 and 1, right? It looks like it's converging in that section. So, yes, looks like it's converging. So, I mean, we could draw a little sketch of this if you want. And okay. So it comes in, kind of goes like this. Like that. That seems pretty good. It seems like it's converging. Okay. Part 4. Part 4 says, do you think the series for inverse tangent of x converges at x equals 1? Can you support your answer with evidence? If you plug x equals 1 in, does it converge? So one way we could do is you could write it out. This is what it'd be when x equals 1. You plug 1 in for all the x values. Right? And now we know the answer to this. The answer of inverse tangent is pi over 4. So if we were to calculate a bunch of these, just look at like partial sums. So that's 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9, right? And pi over 4 is that. You take the previous answer and keep adding stuff to it. Minus 1 over 11. So, I mean, let's write this down. Let's write the decimal. Pi over 4 is 0.83492. And partial sums that we're getting are, I'm sorry, I wrote the wrong thing. 0.785398. So partial sum we got is 0.83492. That was the first 1, 2, 3, 4, 5 terms. 6 terms, we could subtract 1/11. Add 1/13. Subtract 1/15 plus 1/17 minus 1/19 plus 1/21 minus 1/23. So it's getting closer and closer to this value. So I'd say that seems like a pretty good support. Yes, partial sums are getting closer and closer to the value. Now, sort of ironic thing is this is actually how your calculator calculates pi over 4, which we just relied on. Okay, or you could just do it. Okay, exploration number 2. Or 3. A series with a curious property. It says define a function by a power series as follows. F of x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus ... plus x to the n over n factorial And step 1 says find the derivative. Okay, well, f prime of x equals 1 plus 2x over 2 factorial plus 3x squared over 3 factorial plus 4x to the third over 4 factorial plus dot 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 plus n x to the n minus 1 over n factorial plus dot dot dot. And then we could simplify it. 2 cancels out that 2, you have 1 factorial, 3, you got 2 factorial, 4, you got 3 factorial, n, you have n minus 1 factorial. So the derivative, f prime of x, is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus the next term would be x to the fourth over 4 factorial plus dot 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 plus x to the n minus 1 over n minus 1 factorial plus dot dot dot. Okay. Number 2 says find f of 0. Okay, well, f of 0 is the real term. Plug 0 in, you get 1. Okay, cool. Step 3 says, what well-known function do you suppose this function is? E to the x. We talked about this in class. Step 4, use your responses to parts 1 and 2 to set up an initial value problem that the function f must solve. You will need a differential equation and initial condition. Okay, set up an initial value problem. Okay, initial value problem is a differential equation. So if we think it's e to the x, then let's make it e to the x. And the initial value is 1. Okay. Number 5, solve it to prove your conjecture. Step 5. Okay, we separate the variables. Use initial condition. And we get e to the x. All right. 6, graph the first 3 partial sums. What appears to be the interval of convergence for this function? Okay, so kind of like what we did before. Graph the first partial function. So we're going to do e to the x. And then the first, it says 3 partial sums would be 1 plus, okay, 1 plus x plus x squared over x squared over 2. That's the first 3 partial sums. Window. So the first function is e to the x. That's what that looks like. And then here comes the other one, which is a parabola, and it hugs it. And I would say it looks like negative 1 to 1. I mean, that's kind of what we expect usually, negative 1 to 1. 7, graph the next 3 partial sums. Did you underestimate the interval of convergence? So let's try 1 plus x squared divided by 2 plus x to the third divided by 6 plus x to the fourth divided by 24, which is 4 factorial. So that's 3 more, right? No, that's only 2 more. Plus x to the fifth divided by, just multiply that times 5, 120. That's 5 factorial. Okay, so here comes, ooh, it looks like it's hugging it closer than outside of that window, negative 1 to 1, right? I mean, maybe we could see a little more of this graph. So here's the original graph, that's exponential. Here's the first 3 partial sums, which looks like, it's like negative 1 to 1. And here comes the other one. Look, it grabs onto it like at negative 1.5. And I don't even see where it goes. Does it? I think it follows it like really close, like for a long ways on there. So I would say it says, did you underestimate the interval of convergence? Yes, it looks like it's even more than -1 to 1. So that's it. Kind of a fun little exercise to understand these ideas better. Okay. So now let's go on to page 483. And we're going to look at problem 68, which is multiple choice. It says, to which of the following numbers does the series 1 plus 1/3 plus 1/9 plus 1/27 converge? Well, this is a geometric series, right? And a equals 1, and r equals, looks like 1/3. The absolute value of r, is it less than 1? Yep, so it converges, and we just want to use that formula. S equals a over 1 minus r. S equals 1 over 1 minus 1/3 equals 1 over 2/3 equals 3/2, which is answer C. 69. Multiple choice, find all the values for which the series converges. Actually, for the next three problems, you're supposed to use this geometric series. Okay, and so on 69, you're supposed to say, for which values of x does it converge? Well, that's interval of convergence. So it's based off this basic idea of when does a geometric series converge? When the r value, absolute value of it, is less than 1. So going back to last year, AB calculus AB, which borrowed an idea from geometry, solving absolute value inequalities using the rule of positive. The middle is 1, going a distance of 1 away, both sides. So we're at 0 to 2. So we're going to say 0 to 2, which is answer A. Answer A is written like this, but same thing, right? Okay, 70. Which of the following is the function that the power series represents? Well, this one's a little harder. I mean, well, I don't know. What's the A value? A value is 1. If you plug 0 in, you get 1. What's the R value? Well, this right here is the R value, x minus 1. So we can do the sum equals A over 1 minus R. We're going to plug 1 in. We're going to plug R in parentheses to make sure we do distribute the subtraction. And we're going to get 1 over 2 minus x. That's the function. Answer E. 71. Multiple choice, which of the following is a function that the integral of f of t dt represents from 0 to x? So technically, you're supposed to have a different variable in the limits as what's inside. That's why they put t's in here. So we're going to take the function they gave us and I mean, we could write it in open form. Open form, first term is 1, then plus x minus 1, and plus x minus 1 squared, and plus x minus 1 cubed, plus dot, dot, dot. I mean, technically, you're supposed to put t's in here. Okay, now let's see. If we were to integrate that, okay, well, what do we get? We get, and then you integrate, you get the antiderivative, then you plug x in, and then you plug 0 in. So I guess we'll find the antiderivative first. It's going to be t plus t minus 1 squared over 2 plus t minus 1 cubed over 3 plus t minus 1 to the 4th over 4. And then we're going to go 0 to t, 0 to x. So if you plug x in, you get x plus x minus 1 squared plus x minus 1 cubed plus x minus 1 to the fourth, x minus 1 to the n plus 1 over n plus 1 plus dot, dot, dot. Now we've got to plug 0 in, right? For t. If you do that, trying to think right here. If you plug 0 in for all the t's, you're going to get a bunch of little fractions, right? I don't know if I'm doing this right. You can get 1/2 minus 1/3 plus 1/4 minus 1/5. Dot, dot, dot. Okay, let's see if we can figure this out. Okay, I think I've taken the wrong approach. So what we should do is we should say, hey, let's integrate this guy, right? That's the function we said it was equal to, right? So if we do that, it's going to be natural log the absolute value of 2 minus t. You need an extra negative because of that. You can plug 0 to x in, so it's going to be natural log of the absolute value of 2 minus x minus negative natural log of the absolute value of 2, right? That wasn't, the other approach wasn't going anywhere. This is what we want to do. Minus minus plus plus. We could use log rules to combine these together. It's going to be natural log. We could keep the negative in front of the first one and then bring a negative back in here. And so it'd be 2 minus x absolute value over 2. So we do that. And that matches answer D. There we go. I kind of went off in the wrong direction at first. Okay, 72. We're just going to do 72 is another exploration. We're going to just do parts A and B. It says let f of t equal 4 over 1 plus t squared. Let g of x equal the integral of f of t dt from 0 to x. It says find the first 4 non-zero terms and the general term for the power series for f of t centered at t equals 0. Well, we got two approaches. One is we kind of do the approach that we've been doing. A equals 4, r equals negative t squared. The closed form, n equals 0 to infinity is 4 negative t squared to the in power. The open form, you have a 4 and then minus 4t squared and then plus 4t to the fourth minus 4t to the sixth. Because remember, you have a squared here and then you're raising it to the 0 power, the 1 power, the 2 power. Plus dot, 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 plus 4 negative t squared to the n plus dot, dot, dot. So they said find the first 4 non-zero terms and then the general term. So there you go. That's what I did. Alternatively, you could take the approach that we were taking in the notes where you take the derivative of this repeatedly, but it gets bad real quick. So B, so that was part A. Part B says find the first 4 non-zero terms in the general term for the power series of g of x. So remember, g of x is the integral of f of t dt. So we could say, okay, well, let's integrate this guy. 4 over 1 plus t squared dt. That's going to be 4 inverse tangent of t. And then you plug 0 to x in, and you get 4 inverse tangent of x minus 4 inverse tangent of 0, which is 0. Okay, but we want the first 4 non-zero terms of the power series. So what we're going to do is we're going to integrate this guy. Right? We're going to integrate that guy. So if you do that, you're going to get let's see, 4x minus 4x to the third over 3 plus 4x to the fifth over 5 minus, the next one would be minus, we want the first 4. Let's see, fifth. Yeah, this should be a 4x to the sixth over, I messed something up. So it's supposed to be a 6. 7th over 7 plus dot 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 4. I would separate this -1 to the n and t to the 2n. So it's gonna be -1 to the n, t to the 2n plus 1 over 2n plus 1. And then you can put x in. Plus dot dot dot. So if we did t's first and then did 0 to x, when you plug 0 in, all these would have t's and they'd all go away. So this is the first 4 non-zero terms, and this is the general term, and that is it. That's part B. Like I said, part A, you could have made it a lot harder. So we don't want to use that method I talked about in the notes as much as possible because it's a lot of work. A lot of times we can use other functions and having those functions to get their values. Okay. So let's keep going. Next page 492. We're going to start with problem 2. Now, these problems, it says in exercise 1 and 2, construct the fourth order Taylor polynomial at 0. That means centered at 0. So we want fourth order Taylor polynomial. Now, remember the pattern. You guys should be able to write this down from memory very soon. If not, challenge yourself. It is the 0th derivative at the center a, x minus a to the 0th power over 0 factorial. A lot of times that's not written, but I like to write it like that because it's just consistent. And then the first derivative at the center, x minus a to the first power over 1 factorial. And then the second derivative at the center, x minus a to the second power over 2 factorial, and on and on and on. It's kind of a simple, clean pattern. So for 2, they give you f of x equals e to the 2x. So the first thing we do, we did this on the notes, we need to take all the derivatives to make sure we get fourth order. So we need that's like fourth degree, which means you need the fourth derivative. Okay, so the original function, which is like the 0th derivative, is that. The first derivative is 2e to the 2x. The second derivative is 4e to the 2x. The third derivative is 8e to the 2x. The fourth derivative is 16e to the 2x. And that's all we need. And then we need to plug the center in. So you plug the center in, 0, and you get e to the 0 is 1. And the first derivative of 0 is 2. 4. 8. 16. And then we write it. And this is the way you write it. You write P sub 4. Capital P is for Taylor polynomial. P for polynomial. The subscript 4 is fourth order. Not 4 terms. The terms are, that's just going to be 1 and 1. The first term is 1 plus 2. Remember, if a is 0, then you're just going to get x plus 4, x squared over 2 factorial plus 8x cubed over 3 factorial plus 16 x to the fourth over 4 factorial. We can simplify this. That's 2. This is 6. This is 24. We can reduce it and write a cleaned up version of the answer. 1 plus 2x plus 2x squared plus 4x cubed over 3 plus 2 x to the fourth over 3. There we go. Okay. Number 3 says construct the fifth order Taylor polynomial. Fifth order. And this is the function that we have. This one's going to be a little tougher. Now, what you could do is think of this as x plus 2 to the negative 1, so you don't have to do like a quotient rule. I recommend that. So the first derivative is going to be negative x plus 2 to the negative 2, which is going to give you negative 1 over x plus 2 squared. The second derivative is going to be positive 2 x plus 2 to the negative 3, which is going to be 2 over x plus 2 cubed. The third derivative is going to be negative 6 x plus 2 to the negative 4, which is going to be negative 6 over x plus 2 to the fourth. The fourth derivative is going to be 24 x plus 2 to the negative 5, which is going to be 24 over x plus 2 to the fifth. And last one, fifth derivative, negative 120, x plus 2 to the negative 6, negative 120, x plus 2 to the 6 bar. Okay, so those are all the derivatives. Then we got to plug the center in. It says it's centered at 0. So we got to plug 0 in. We get 1/2. And we get negative 1/4. And we get 2/8 or 1/4. And we get negative 6 over 16 or negative 3/8. This is what I was saying you could have done on like problem 72 on the other page. We kind of have, I think, yeah, don't really have to in these. Okay, so what do we get? 2 to the fifth, 8, 16, 32. Times another 2 is 64. You take an 8 out of all these, negative 15 over 8. Okay, so those are all the values we need. I mean, it's tedious. It's not like hard. It's tedious. So then we're going to plug them in. P sub 5x. And so it's going to be first one, 1/2 times 1 over 1 plus negative 1/4 times x over 1 factorial plus 1/4 x squared over 2 factorial plus negative 3/8 x cubed over 3 factorial plus 3/4 x to the fourth over 4 factorial plus negative 15/8 x to the fifth over 5 factorial. Okay. I'm going to clean it up. Now this is 2, 6, 24, 120. You know, I almost wish we had left them unfactored or unreduced. First term is 1/2 minus 1/4 x. That's easy. Plus 1/8 x squared. That's easy. This is 6. So it's going to be minus x cubed over 16. See if I just left it like this. That would have been easier. I think I'm going to take advantage for the next one. Plus, this one was 24 over 32 divided by, it's just going to be 1 over 32. It's going to be x to the 4th. And then this one was 120. Cancel out with the 120. 1 over 64, x to the 5th. Okay. Alternatively, and we could also, here's the funny part. If it's easy and if it's already something that's kind of written in the form of the sum of a geometric series, why don't we just be like, oh, a equals 1 and r equals, you got to rewrite this as 1 minus something. I don't know if this is going to work. This was 2. It would be x negative x minus 1. And maybe that's not going to work. Yeah, I guess not. Okay, closed form. Well, that would be the infinite series. Does it say do that? Oh, it says fifth order Taylor bond and the Taylor series. So the Taylor series, a lot of times I think they call it, you put a T for Taylor series. So that would be the whole thing. So first term, what's the pattern here? If we put n equals 0, n equals 1, n equals 2, let's find the pattern. It looks like there's a negative 1 to the nth power. That's separate. And then it's it's 2 to the first, 2 squared, 2 cubed, right? So it's 2 to the power, 1 more than n. So it's 2 to the n plus 1. And then there's an x. X to the n. X to the 0, x to the first. So there's a bunch of patterns going here. This is the Taylor series. That's a fifth order Taylor polynomial. Okay. Five. It says, in these exercises 512, use the table of the Maclaurin series on the preceding page to construct the first 3 non-zero terms and the general term of the Maclaurin series generated by the function and given by the interval of convergence. Okay, so here's a new interesting thing that we can do. We could do this the long way, but they're saying, hey, use those list of series. So the one in that list that makes sense here is this one. So I'm going to write it down because we're going to use it. So this is the shortcut. So write it down. This is allowing you to do less work. So write it down. And I'm going to give you guys this list. Okay. So that's the series. So guess what we can do? Check this out. If you want to do sine 2x, then it's just like plugging 2x in everywhere you see an x. But anything that's happening to the x has to happen to the 2x. So sine 2x equals 2x minus 8x cubed over 3 factorial plus 32x to the 5th over 5 factorial. So the 2 gets raised to that power because that's what's going in for the x. But that's like so fast. That's so much faster than doing all the derivatives of this. So it said first three non-zero terms and the general term. So the general term, you plug 2x in. And if you look back, it converges for all real x. So that's kind of crazy. It's not restricted, -1 to 1. There you go. Okay. That's okay. Number 8, 7x e to the x. Do you want to do this one the long way? No, you don't. Product rule after product rule after product. It's gonna. I mean, you can do it, but I mean, here I'll do it two different ways. Shortcut. Maybe even if you don't want to do it the long way, maybe just watch me do it. But shortcut is, hey, we have this function for e to the x, right? On that page, we're going to memorize it. And this one's for all real x also. Okay? So what we could do is say, oh, well, let's just multiply e to the x by 7x. Just distribute a 7x to all this. 7x plus 7x squared plus 7x cubed over 2 factorial. That's the first three non-zero terms. 7x to the n plus 1 over n factorial plus dot, dot, dot. Done. I mean, that's the way to do it, right? Okay, the longer way, which we're going to avoid as much as possible. As much as possible. But sometimes we can't. The long way is say, okay, that's your function. And let's find the derivative of it. You got to do product rule. And then the second derivative. You got to do product rule again. And then you got to take derivative of this. And then third derivative. You got to do product rule again. And then we got to do derivative of this. And the derivative of this. Okay? All right. And then you would plug 0 in because it says Maclaurin series. All those series on that page are Maclaurin series. So these are Maclaurin series, which means they're centered at 0. So you would get 0, 7, 14, and 21. And then you would plug them into that pattern for Taylor polynomials. It's the first one times x is 0th power over 0 factorial. That's 1, but it's 0 plus 7 times x to the first over 1 factorial plus 14 x squared over 2 factorial plus 21 x cubed over 3 factorial. And then we could clean it up. We say, okay, well, that's going to be 7x plus 7x squared plus this is going to be 6. So it's going to be 7x cubed over 2. Look at that. Same thing. But now you got to find the nth term. So you probably want to simplify it and see if you could find a pattern. So it looks like it's going to have a 7 x to the n plus 1 over, and it's a little harder to determine this pattern, but it's going to be n factorial. So which way would you rather do it? Just take this and distribute 7x to it all? Or take all these derivatives, value them at 0, put them into this pattern, which is, this is all straightforward work. It's just a lot of work. Okay. Anyways, hopefully you're starting to see some things here. Sometimes we've got to do it the long way, but a lot of times we don't. Okay, 15 says find the Taylor polynomial of order 3 generated by f. And part A is centered at 0. So the function is f of x equals x cubed minus 2x plus 4. Now this one, we can't do a shortcut. So we got to take the derivative. And the derivatives on this one are a lot easier than the last one. Take the derivative. Take the derivative. They said order 3. So you need the third derivative. Now, for part A, they said centered at x equals 0. So we plug 0 into all these, including the first term. A lot of people always forget that one. It starts with the zero, like the 0th derivative. Some people just think, oh, I got to start with the first derivative. All right. So those are those values. So then we're looking for the third order Taylor polynomial. So P sub 3. Plug the first value in, 4 times x to the 0th over 0 factorial plus negative 2, x to the first over 1 factorial plus 0, x squared over 2 factorial plus 6, x cubed over 3 factorial. 0 term just drops out. So P sub 3 third order Taylor polynomial is 4 minus 2x plus x cubed. That wasn't so bad like last one. B says centered at x equals 1. So this is where things get a little more interesting. 1, you got to plug 1 into all these. So that's going to be 3. We're going to get different values. It's going to be 1. It's going to be 6. And that's going to be 6. So you can get those values. Now I'm going to write B down here. Because what you got to do, people are going to forget this, is it's going to be the value times x minus the center. Now the first one just drops out, but I like to write it just to like get that pattern going. 1 x minus 1 to the first, 1 factorial, plus 6 x minus 2 squared over 2 factorial, plus 6 x minus 3 cubed over 3 factorial. Now the nice thing is you get to leave these in here with those powers, okay? You don't have to like totally simplify it, but we're gonna have 3 here, plus x minus 1, plus 3 x minus 2 squared, plus x minus 3 cubed. This is 6, so those cancel. This is 2, so that would just 3. So now to make Lorentz series centered at 0, this is Taylor polynomial centered at 1. Oh, you know what? I made a mistake. There should be a 1 here. I don't know. How did I start writing different numbers there? Okay. All right. That's it. Good stuff. Put in your time now, and it'll pay off. Put in the time now, and it will pay off.